wonderful concepts based on baseband digital communication like PCM, DPCM, delta modulation, binary symmetric channel. So I'll discuss the most expected questions based on these topics. Right. So this is my introduction. So I teach communication systems and signals and systems, and this is my Telegram channel, Telegram group. So if you wish to ask me any doubts based on these two subjects, you can definitely contact me on this group. Okay. Right. So let us start with the first question. Okay, wonderful. Right. So this is the first question. So a sinusoidal message signal is applied to a n-bit PCM system. The maximum quantization error should be less than or equal to 0.2% of peak amplitude of the signal. Find the optimum value of n. Find the optimum value of n that can be used in the PCM system. Read the question carefully. Read the question carefully. I'll wait for a minute or two, and then I'll start solving the question. So I've discussed this model in the last 8 sessions, in one of the 8 sessions, last 8 sessions. So if you have attended my sessions, this should be a cakewalk question. Just understand the question carefully. You should be able to solve it easily. Read the question, understand the question carefully, and apply your basics. Right, there is a condition given. The maximum quantization error should be less than or equal to, it is less than or equal to 0.2%, 0.2% of peak signal amplitude, peak amplitude of signal, peak amplitude of signal, right? Now, what do we know about maximum quantization error? What do we know about maximum quantization error is it is equal to half of the step size. It is equal to half of the step size. So let us put this as it is. And we know the basics of step size. Step size is given as voltage swing, which means the range of voltages possible for the signal, which we can find using the highest voltage minus lowest voltage, divided by 2 to the power of n. So this is how you can find step size. So if you want to find voltage signal or voltage swing, then definitely you should know the highest voltage in the signal and lowest voltage in the signal. And they have given one information that it is a sinusoidal message. Since it is a sinusoidal message, let us assume something about the signal. Let's say it is something like AM cos omega mt or AM sin omega mt. Sinusoidal means it can be cos or sine with any phase. So let us assume this way. Because why I'm assuming that this way is because we will assume some amplitude, some peak amplitude, so that we can get voltage swing, and peak amplitude of the signal is also being used here. So that's why it's better to assume the signal equation, because they have anyway given it as sinusoidal message. We don't know the frequency of the message, that's fine, that's why we have not written any frequency here, right? So now voltage swing, we can write it as, what is the voltage swing of the signal? The highest voltage is AM, lowest voltage is minus AM, so voltage swing is 2 AM is the voltage swing divided by 2 to the power of n, that is delta, and another by 2 is there, so it is 2 into 2 power n. So it is delta by 2. Delta we can find using this. Voltage swing is 2 AM. I have substituted that. It is less than or equal to 0.2%. Percentage, let's convert it into normal scale. How do you convert into normal scale? Percentage, if you want to convert into normal scale, just divide it by 100. 0.2 divided by 100 into peak signal amplitude. Peak amplitude of the signal, we have assumed it as AM cos omega mt. So in that assumption, peak amplitude is AM. Now let us cancel the things that are possible to be cancelled. So we can cancel AM, we can cancel this 2, and what is left is, this is 2 power n into the numerator. Let's take it into the numerator. Similarly, we'll take it the same thing on, we'll exchange the numerator and denominator. When you exchange the numerator and denominator, sign also changes, inequality sign also changes. So 0.2, if it comes to the denominator, it will become 5. 0.2, if you reverse it, it will 1 by 0.2 is 5, so it will become 500. I hope you have understood this step, or else if you are confused, so just bring this onto this side and 2 power n onto the other side. That is how this is how much we are going to get. So 2 power n is greater than or equal to 500, which means n greater than or equal to logarithm of 500 to the base 2. This implies, what is n value? If it is 512, it is 2 power 9. 2 power 9 is 512. So, but so this is not 512. This is less than that. So which means n is around somewhere around 8.9 or something like that. I don't know the exact value, but somewhere it is around 8.9. But n is number of bits. Number of bits cannot be a non-integer. It should be an integer. So what is the closest integer that we can choose? N, the minimum value possible, the optimum value of n is 9. The best value of n possible is 9. N, you can say optimum value of n possible is 9. Why? Because we can choose 10 also to satisfy this condition. Quantization error will be less than 0.2%. But as you increase n value, bitrate increases, and hence bandwidth requirement also increases. So the minimum value of n will be more advantageous for us. Satisfying this condition, the minimum value of n possible is 9. Okay. Right. Very good, Surajit. Let's move on to the next question. Look at the question. A PCM system is designed for signals taking voltages from -2 to +2 volts. A signal sine of 2 pi 8000 t plus pi by 4 is applied to the PCM system. Find the SQNR. I'll wait for a minute. You can try it out. If you have the right basics, it should not be a tough question. I have discussed this model of question in my previous sessions. Right, so let me start doing it. If you are doing, you can keep continuing. So SQNR, signal to quantization noise ratio. We can't blindly use the formula because they are saying that the system is designed for signals taking voltages from -2 to +2. The system is designed, means the quantizer is designed for signals which take voltages from -2 to +2, which means they are telling us about voltage swing based on which the quantizer is designed. Okay, quantizer, when we are designing, we will have an assumption about the signals. Okay, signal takes the signals take a certain range of voltages, and based on that only we design the quantizer. Without any assumption about signals voltages, we can't design the quantizer. So that is what they are saying. Is a PCM system is designed for signals taking voltages from -2 to +2. Signals voltage are relevant only for quantizer. For sampler, it does not need that information. Only for quantizer, this information is required. So they are trying to give us the information of voltage swing using which quantizer is designed. Voltage swing used in the design of quantizer is 4 volts, and they are saying the signal is given is sine of 2 pi 8000 t plus pi by 4. But here, what is the voltage swing of this signal? So this is voltage swing of quantizer that is being designed. Mind this is a little tricky thing to understand. This is voltage swing of quantizer that is being designed because they have assumed that the signals are taking voltage from -2 to +2. But suddenly you have applied a signal which does not have that voltage swing. But that's fine. You can't change the design of the quantizer. Once it is designed, that's it. We can't change it. So even if you apply any signal, the quantizer design will be exactly same. That will not change. But signal has changed, na? So signal power will change, no? When we have derived that formula for SQNR as 6n plus 1.8 dB, it is, the basic assumption is you are designing the quantizer with a voltage swing which is same as the message signal voltage swing, but here it is different. So that's why we can't blindly use the formula 6n plus 1.8. Okay, but we have the basic procedure. You can find the signal power, you can find the quantization noise power, and just you can find the things. You don't need the formula. Whenever the problem looks different from the derivation that we have done, different from the assumptions that we have used in the derivation, then definitely you have to go from the basics. Start with SQNR. How to find it? Find the signal power, find the quantization noise power. Signal power divided by noise power. quantization noise power. And we know what is the signal power. Signal is given as sine to 8000 pi t. So peak amplitude of the signal is 1 unit. Peak amplitude of the signal is 1 unit, that is nothing given, which means 1 unit. So power of the signal is 1 square divided by 2. Half units is the power of the signal. Right? How about quantization noise power? Let's calculate that. That is crucial. So if you want to calculate quantization noise power, you can find it as using expectation of QE square or expectation of x minus y whole square. But there is no information given about the signal. I told you that when signal is given as having uniform PDF, then definitely quantization error also will have uniform PDF for sure. Okay, and when the signal is given as sinusoidal, which means they have given some deterministic signal, not only sinusoidal signal, other deterministic signals also. In these two cases also, we are going to assume quantization error as uniform, having uniform PDF. In these two cases, it is just assumption. But in the first case, it is the exact actual thing that is happening. In the last two cases, we are assuming quantization error is going to have uniform PDF. What if quantization error is having uniform PDF? We have derived a formula for quantization noise power. When quantization error is also having uniform PDF, expectation of QE square, we can easily found, and the result in that case is, under these assumptions, quantization noise power formula is del square by 12. See this one? When signal is having uniform PDF or sinusoidal or deterministic, you can assume quantization error is uniform. And whenever quantization error is having uniform PDF, quantization noise power will be del square by 12. You can always use this funda under these conditions. If it is different, then you have to go with the basics. I have discussed those are the tricky models that are possible. If the model is different, like if they have given signal having a PDF other than uniform PDF, then problems will become little tricky. But I have told you the procedure to solve such problems. Okay, it is again same basics, expectation of x minus y whole square. That expectation of x minus y whole square, you have to divide it into different quantization regions, then it will become an easy problem. So if you want, you can refer to questions on PCM, the second class practice session on PCM. In that I have discussed in very detail. Right, so quantization noise power, since there is no information about the signal, you can assume the quantization error is having uniform PDF, and quantization noise power can be written as del square divided by 12. Step size corresponds to quantizer. Step size corresponds to design of quantizer. Okay, how the quantizer is designed? Based on voltage swing and number of bits. Right, since delta is step size corresponding to design of the quantizer. Once the quantizer is designed, we can't change anything about it. What we can't change about it? Step size can't be changed. Okay, so step size is voltage swing divided by 2 to the power of n whole square divided by 12. And what is the voltage swing of the quantizer? Quantizer is designed with a voltage swing of 4, but the signal is having a different voltage swing. Fine, but signal's voltage swing we should not take into consideration because the quantizer is designed according to these voltages. Okay, once the quantizer is designed with these voltages, we can't change the design of the quantizer. Once it is designed, it's fixed. So it is 4 volts divided by 2 to the power of n. Okay. Find the SQNR. So n value is not given, right? Okay, let me give you the n value here. An 8-bit PCM system. Let me give you as an 8-bit PCM system. So n value is also given. It is 2 to the power of 8 whole square divided by 12, which is equal to, so this is 2 power 2. If you cancel it, it is 1 by 2 to the power of 6. This is 2 power 6 whole square is 2 power 12 divided by 12, which is equal to 1 by 2 to the power 14 into 3. 12 I am writing it as 4 into 3. 4 means 2 power 2. If you add to this, it will become 2 power 14 into 3. Right, so we got quantization noise power. So let us substitute it here. It is 1 divided by 2 power 14 into 3. So everything goes into the numerator and it becomes 3 into 2 to the power 14 and 2 cancel, it becomes 2 power 13. We got SQNR as 3 into 2 power 13. So if you apply logarithm, so it is 10 log, because we are dealing with Power ratio, we have to apply 10 log. If you are dealing with voltage or currents, you can apply 20 log. So it is 10 log 3 into 2 to the power of 13. Okay, so this is 10 log 3 to the base 2 plus 13 into 10 log 2. To the base 2. Sorry, it is base 10, no? It's not base 2, my mistake. Base 2 we use only in the information theory, not here. Here it is only base 10 when we are converting power or power, energy or current into dB scale. When we are converting into dB scale, we always use logarithm to the base 10 only. 10 log base 10 13. This 13 is coming here. This 13 is coming here into 10 log 2 to the base 10. So 10 log 3 to the base 10 is somewhere around 10 log 4 is 6 dB. It is somewhere close to 4.5 or 5 dB, this part, around approximately 4 to 5 dB. And how about this one? 10 log 2 to the base 10, we know it is 3 dB. So 3 dB into 13 is 13 3 is 39 dB. Plus this is somewhere around 4 dB or something like that. 4 plus around 4 and a half, 4.5 something like that. I don't know exactly, but 10 log 3 is somewhere around 4 to 4. It is between 4 and 5. So roughly it is around 43 dB, 43.5 dB approximately. Okay, very good. Hi Tabu. So this is the answer for the second question. Right, next question. So this is minus 4 to plus 4, okay? This is minus 4 to plus 4. A signal of bandwidth 4 kHz is sampled at 150% higher than Nyquist rate and then encoded using an 8-bit PCM system. If the signal takes voltages from minus 4 to plus 4 volts with uniform probability, find quantization noise power and signal to quantization noise ratio. Wonderful. So solution for the question, let's do it. They are asking us about quantization noise power. So when you want to find quantization noise power, we know a formula for quantization noise power, which is del square by 12, and that is not the formula always. That is the formula only if the quantization error is having a uniform PDF. So see the information regarding signal. Regarding the signal, they said that the signal is having uniform probability. Yes, whenever signal is having uniform PDF, quantization error also will have uniform PDF. If the quantization error is having uniform PDF, definitely we know the formula for quantization noise power as del square by 12, which can be used. This can be used whenever quantization error is having uniform PDF. Right, so we can use this formula. So del, how much is del value? Minus 4 to plus 4. Voltage swing is 8 volts divided by 2 to the power of n. 2 power of n is given as 8 bits. 2 power 8. Voltage swing divided by 2 power n whole square divided by 12. So this is equal to, this is 2 power 3, 2 power 8 cancel, it is 1 by 2 power 5. So it becomes 1 by 2 power 10. When you square it, it becomes 2 power 10 into, so it is 4 into 3. It is equal to 1 by 2 to the power of 12 into 3. Okay. Then we got quantization noise power. So if you want, you can convert it into dB scale. If you convert it into dB scale, it is 10 log 2 to the power of minus 12 into 1 by 3. So 10 log 2 to the power of minus 12 plus 10 log 1 by 3 to the base 10. So this is minus 12 aside. 10 log 2 to the base 10 is 3 dB, that much we know. So 10 log 1 by 3 we can write as 3 power minus 1. So minus 1 comes here, and we can write it as minus here. So 10 log 3, just now we have discussed, log 3 is somewhere around 4 to 5. I don't remember the exact number, but it is somewhere around 4 dB or 4.5. Let me assume 4.5. It might be around 4 to 5, which is equal to 12 3 is 36 plus 4. 36 plus 4 is 40 minus 40.5 dB. Okay, right. So we got quantization noise power. So how about SQNR? If you want to find SQNR, first you should know signal power, and we already have calculated quantization noise power, right? So if you want to calculate signal power, and signal is given as random signal, and signal is given as random with uniform PDF. It is having probabilities values. It takes values from -4 to +4 with a height of 1 by 8. This is the PDF of the signal. Let us assume if the signal is x, this is fx of x. Since this is for uniform PDF, for this one mean value is 0, so mean value or variance will be same because mean is 0. For this case, mean value is 0, hence variance and mean square value will be same. And the formula for mean square value is, or variance is, b minus a whole square by 12. b is 4, 4 minus of -4 is 8, 8 square by 12. That will be the noise power. So if you want, you can calculate using expectation of x square and the integration of x square into fx of x dx. You can substitute this, you can find it. But if you know the formula for finding noise power in for a uniform PDF, then you can substitute you can use that formula to find mean square value easily. Okay, if you don't remember the formula as b minus a whole square by 12, yes, you can go with the basics. Expectation of x square, you can find integration of x square into fx of x dx. You can use this fx of x in that substitution. So it is 8 square, 8 8 is 64, 64 by 4, it will be 16 by 3, right? Yes, it is 16 by 3. So 16 by 3 is the signal power, and this part is 1 by 2 to the power of 12 into 3. So I think we can cancel this 3 part. This 2 power 12 goes to the numerator, into 16 is 2 power 4, and it becomes 2 power 16. So if you apply logarithm, is 10 log 2 power 16. It is very easy to convert this part. So 16 aside, so it is 10 log 2 to the base 10. 10 log 2 always results in 3 dB. Log 2 to the base 10 is 0.3. It is 10 log 2 to the base 10 is 3 dB. So 16 aside, it becomes 3. 16 3s are 48 dB. I hope your answer matches with mine. Okay. Right, next one. A signal takes voltages from -0 to 8 volts. It is 8 volts with distribution as shown in the figure. This is probability distribution function of the signal. Let's say if it is x, this is fx of x. This is the PDF of the signal, which takes voltages from 0 to 8. It is given that it is also, this graph also shows that it is taking voltages from 0 to 8 with these probabilities. So here they have given the information as b, so we have to find b as well to know the height. Okay, and as shown in the figure is quantized using a 1-bit uniform quantizer. It's a 1-bit quantizer, it seems. 1 bit means it's 2-level quantizer. Only 2 quantization levels are there. If 2 quantization levels are there, only 2 quantization regions should be there. Only 2 quantization regions. 2 quantization regions means it should be 3 boundaries. 3 boundaries, 2 regions, 2 quantization levels. Right, find the quantization noise power and SQNR of the quantizer. Okay, right. So first let's find, if you want to find SQNR, you have to find signal power. You have to find signal power and then quantization noise power. Now both of them are tricky. Now this is one of the tricky problems that can be given. So signal power and quantization noise power both are not straightforward because that is not uniform PDF to apply some formula. There is no way of applying formula. You have to find everything directly using the basics. So let's find it. This is a good question, little challenging question also. Signal, SP means signal power. Signal power is equal to expectation of x square. This is how we find it, and expectation of x square is given. But if you want to find this, the formula for this is integration of x square into fx of x dx. So if you want to substitute that fx of x here, you should know these heights, na? So let's find those heights. So we have a property of PDF. Area of PDF is equal to 1. Area of PDF should be equal to 1. So find the area of this. This rectangle area is 4 into 4 is 16b, plus this part is 4 into b is 4b, which is equal to 1. The total area is this rectangle part area is 4 into 4 is 16b, plus this only this part is 4 is the width and height is b, 4b. 20b is equal to 1, b equal to 1 by 20, which is 0.05, okay, or 1 by 20 you can say. So b is 1 by 20, so this part is, this is 1 by 20, and this part is 4 times 1 by 20 is 1 by 5. The height here is 1 by 5. So you can write the equation as 1 by 5 for 0 less than x less than 4, and the equation is 1 by 20 for 4 to 8. So this is the PDF equation, and the equation of the PDF is 0 for other values of x. Let's substitute that here. So the equation is integration from 0 to 4 x square into equation of fx of x is 1 by 5. It is the equation is 1 by 5 only in the limits from 0 to 4 dx, plus in the limits from 4 to 8, in the limits from 4 to 8 for values of x from 4 to 8, the height of the PDF is 1 by 20, or the equation of the PDF is 1 by 20 dx. It is a simple calculation now. So this is equal to 1 by 5 aside, this is x cube by 3, limits from 0 to 4, plus 1 by 20 outside, x square integration is x cube by 3, limits from 4 to 8. So this is equal to, so 1 by 5 into 3 x cube, 4 cube, it is 4 cube minus 0 cube, it will become 4 cube only, plus here it is 1 by 20 into 3, 1 by 20 into 3, upper limit is 8 cube, 8 cube minus 4 cube. So this is equal to 4 cube is 4 4 so 16, 16 4 so 64, 64 divided by 15, plus 8 cube is, okay, 2 cube aside, or else 4 cube if you put it outside, if you can take 4 cube common, it will become 2 cube minus 1 divided by 20 into 3, or 4 into 5 into 3, 4 into 15. I am writing 20 as 4 into 5, 5 into 3 as 15. Why I am taking common 4? Because 4 I can cancel, 1 4 I can cancel, so we can cancel that 4 here also. Little calculations are involved definitely. So this is equal to 64 by 15 plus, I think this is correct only, 4 cube common, so it will be 2 cube minus 1, yes. So 1 4 gets cancelled, it becomes 4 square, 4 square is 16, 16 and this is 7, and how much is 16 into 7? 16 5s are 80, 116, right, divided by 15, correct. So 116 plus 64 is 180 divided by 15. I think 15 we can cancel it, no? It is 12 times. Am I correct? I think that should be correct. Okay, my mistake here. It's not 116, it's 112. 16 sevens, right? This is 7. 16 sevens are 112. I've written it as 116 by mistake. Right? 16 6 are 96. 16 sevens are 112. Yes. So 64 plus 112 is 176. 176 by 15. Yes, we can leave it like that, or we can also simplify. 15 tens are 150. 15 11s are 165. It is approximately 11 point something. 11.7 or something like that. 11.7 or 11.8, something like that. So if you want, you can convert that into dB scale. So it will be roughly around 10 dB. 10 is 10 dB. So it is 12. So 12 means roughly it will be somewhere around 11 or 12 dB. Fine. So we got the signal power. So we have to find the quantization noise power. So to find quantization noise power, first we should know the quantizer characteristics. Na? Let's plot the quantizer characteristics. It's very simple actually. Because it is 1 bit, it becomes easy. I'm plotting here because of lack of space. Right. So only 1 bit. So 2 levels and 2 regions. So let us find step size so that it will be more clear for you. So delta is equal to voltage swing. What is the voltage swing? Highest voltage minus lowest voltage is 8 volts. 8 minus 0 is 8. Divided by, so it's only 1 bit. So 2 power n is 2 power 1. It is equal to 4 volts. Step size is 4 volts. So how many such steps will be there here? Only 2 steps. So 0 to 0 is the one boundary. 4 is another boundary. 8 is another boundary. There are only 3 boundaries. 3 boundaries. Because only 1 bit, there are only 2 levels. With 3 boundaries, only 2 regions are formed. 2 quantization regions. And for each quantization region, 1 level. And what is the quantization level that we choose? We generally choose the midpoint. So let us choose the midpoint. What is the midpoint of this? 0 and 4. It is 2 units. So the quantization level that we use for 0 to 4 volts is 2 volts. Is 2 volts. And from 4 to 8, for 4 to 8 the midpoint is 6. So the quantization level that we use here is 6. This is 2 and this is 6. So this is input X versus output Y of quantizer. This is output of quantizer. This is output of quantizer. X is input to the quantizer. Okay. Now we have the quantizer characteristics. Once we have quantizer characteristics, let's find the quantization noise power. So quantization noise power is equal to, it is expectation of QE square. QE is the quantization error voltage or quantization noise voltage, you can say, which we can also write it as X minus Y whole square. So this is here, Y is also random. So these models I've told you a technique, and the technique is X minus Y is, it is looking like 2 random variable case where you have to use second order PDF, which is not possible for us to use. So that's why what we have to do is this expectation of X minus Y whole square only, let us divide it into multiple regions. Each quantization region, do this separately, because for each quantization region, for this quantization region, Y is fixed. For this quantization region, Y is fixed. For every quantization region, Y is like a constant. But overall, Y is not constant, Y is random. But for each quantization region, Y is constant. So that's why do this expectation of X minus Y whole square for each quantization region. Expectation of X minus whole square for X from 0 to 4. For X from 0 to 4, what is the Y? For X from 0 to 4, Y is 2 units. So we can substitute the 2. So basically X minus Y, X minus Y whole square, this we have to do for all values of X from 0 to 8. That what we are doing is, we are doing it separately for each region. For 0 to 4 once we are doing, the same thing we are doing again, and we are adding up. X minus whole square for X values from 4 to 8. Instead of doing the integration for all voltages from 0 to 8, we are doing it part by part. 0 to 4 once and 4 to 8 next. So that the integration will become easy. See this one, Y value is fixed because you are choosing only X values from 0 to 4. And since you are choosing the X values from 4 to 8, Y value is fixed as 6. Very easy, right? Now we can use simple expectation. How we find? The same way we have found here, we can do the same way. So it is integration of X minus 2 whole square into Fx of X. What is the PDF of X? For 0 to 4, the PDF of X is having a height of 1 by 5. It is having a height of 1 by 5 dx. The limits are from 0 to 4 because we know x runs from 0 to 4 in this case, plus integration from 4 to 8, the second case, x minus 6 whole square into what is the height from 4 to 8? The height of the PDF from 4 to 8 is b. So integration of x minus 6 whole square into fx of x dx. In place of fx of x, we are substituting 1 by 20. Okay, right, wonderful. Let's do the integration quickly. So it is 1 by 5 outside, x minus 2 whole square, integration is x minus 2 whole cube divided by 3, limits from 0 to 4, plus x minus 6 whole cube divided by 3, and 20 is also there, limits from 4 to 8. So we have to substitute the values and see what happens. So if you substitute here, yeah, 4 minus 2 is 2, 2 cube is 8, and if you substitute 0, that will become minus 2 whole cube, which is minus 8. 8 minus of minus 8 is 16, so it becomes 16 by 5 into 3. This becomes 16 by 5 into 3, which is 15, plus, let's see what happens to this. The denominator is 20 into 3 is 60. What happens to the numerator? It becomes 8 minus 6 whole cube, which is 2 cube, minus 4 minus 6 whole cube is minus 2 cube. So the numerator will be again 16 only. 16 divided by, the denominator is 20 into 3 is 60. Yeah, but we can separate that 4 outside. We can write this as 4 into 5. Okay, or else I'll write it as 60 only. I'll write it as 60 only. But we can cancel the things, na? 4 4s is 16, and this is 4 15s. So this becomes 4 by 15, correct? This becomes 4 by 15. 16 plus 4 is 20 by 15. 20 by 15 is 4 by 3. Yes, we got signal power, and we also got quantization noise power. Okay, so we can substitute the things here and we can get the answer. So finally the answer is, so signal power we got it as 176 divided by 15 divided by 4 by 3. I believe I have not done any calculation mistake. Because of lack of space, I'm not able to write everything in detail, the calculation part. So you can do the calculations on your own. You should be getting similar answer. So 3 1s, 3 5s. So this is equal to 176 divided by 5 4s are 20. So which is equal to 2. If you cancel, it becomes 2 8s are 16. 84, right? 84 or 88? 88, yes. So this becomes 8.8. Correct? So SQNR is 8.8. So 8.8 into dB scale you can convert. So it will be less than 8 is like 9 dB. Yeah, somewhere around 9.5 dB. This will be somewhere around little greater than 9 dB. You can apply 10 log to that. Fine, that is the answer. Do it carefully. Okay, so this is a little tricky problem. Why it is tricky? Once you know the basic idea to do it, then the tricky part is the calculations. The calculations are a little tricky. They take time. There is a possibility to make mistakes in calculation. But understand the procedure for this problem. This is the trickiest problem possible in PCM or in quantization, you can say. So to make the problem a little easier, I have taken only 1-bit quantizer. In exam also, they will not take a higher level quantizer because the problem will become highly difficult, which we will not be able to solve within 5 minutes also. So that's why generally they will take quantizer characteristics so that it will become easy to calculate. Right, wonderful. So next one. So I have covered the expected questions from PCM system or quantization and PCM together, you can say. Now let us come to the delta modulation. Do it. Come on, make it fast. A message signal is given, and they are saying it is being encoded using a delta modulator. The sampling rate used is given. The sampling rate used is given. Is it possible to design an optimum value of step size so that there is no distortion by the delta modulator? So if you want no distortion by delta modulator, the condition for no distortion, let's see. maximum magnitude of the slope of the signal should be equal to delta by Ts. This is the condition for no distortion. So if you want to know distortion, what should be happening? This is a constant. Hence, if this is also a constant, if this is also a constant, then only we can have, then only it is possible to design an optimum value of step size so that there is no distortion. No distortion case is possible only for signals which satisfy the condition that this is a constant. So let us see that signal. So that signal is looking a little complicated, but let us plot it, then it will look easy. So 10t, so it is a constant slope signal. 10t, it looks something like this. So it exists from 0 to 1. So at t equal to 1, it becomes 10 units. 10 units is the height. Next, at t equal to 2, at t equal to 2, because this signal exists only from 0 to 1, and this signal exists from 1 to 2 because it is multiplied with a rectangle here. This represents a rectangle. So 20 minus 10t, if you plot it, it is going to look like this. So this is how it looks like. So the slope here is 10 units and the slope here is minus 10 units, but it exists only in the duration 0 to 2. In the duration it exists. Is the magnitude of slope constant? Here it is 10, here it is, slope is minus 10, but magnitude is 10 only. So in the duration in which it exists, it has a constant magnitude of slope. So the answer is yes, it is possible to design. The answer is yes, because in the duration in which it exists, it has constant magnitude of slope. It need not have constant slope, it should have constant magnitude of slope. Right, if S, they're asking us to find the optimum value of step size. So let us substitute this. What is the magnitude of slope? Sorry, it's not my mistake here. It's not maximum magnitude of slope, it is just slope, magnitude of slope. It's not maximum. That maximum we use only for for having no slope overload distortion. For no slope overload distortion only we use maximum magnitude. But here it maximum or the constant magnitude, both are same here, because we are expecting a signal to have constant magnitude. Right. So the condition for no distortion is magnitude of slope should be equal to delta by Ts, not maximum magnitude of slope. Right. So maximum magnitude of slope, sorry, magnitude of slope of the signal is 10 units. It is equal to delta by Ts, or we can also write it as delta into Fs. So 10 equal to delta into, what is Fs given? They have given the sampling rate as 400. We can substitute that here. So delta is equal to 1 by 40, right? 1 by 40, or we can also write it as 25 millivolts. Okay. Yes, 25 millivolts. So if you design the step size as 25 millivolts, then the staircase signal that we are going to have with the delta modulator, that will follow the signal correctly like this. If you take bigger step size, it will not follow. If you take smaller step size, it will not follow. Similarly on the other side also, something like this. If you choose that step size, if you choose a bigger step size, you will get granular distortion. If you choose a smaller step size, you will get slope overload distortion. Right, next one. See this one? Here also same question, but the signal is different. You can easily guess the answer here. How? Slope here is 10 units and the slope here is minus 5 units. Slope is 10 here, slope is minus 5. For the 0 to 1 second, the slope is 10, and for 1 to 2 second, the slope is minus 5. Magnitude of slope is 5. Here the magnitude of slope is 10. So magnitude of slope is not same for all the time it exists. If the magnitude of slope is not same, we cannot design a step size which will avoid all the distortion. In the previous case, it was different. In the previous case, it was different. See this one? 10 slope, 10 magnitude of slope is also 10 here. Minus 10 is the actual slope, magnitude of slope is 10 and 10. But whereas here, it's different slope. So that's why it is not possible. The answer is no. Since the answer is no, we don't need to find the step size because it does not exist. Right, next one. An SI signal is sampled at the Nyquist rate and encoded using a delta modulator. Is it possible to design an optimum value of step size so that there is no distortion by delta modulator? Is it possible? No, right? For a sinusoidal signal, magnitude of slope is equal to, just differentiate it, you get it as minus 20 into 4000 pi into cos of 4000 pi t plus pi by 8. Is it constant? No, it is dependent on time. As time changes, this cos magnitude changes, and so magnitude of slope is not constant. Hence, it is not possible to design a step size so that no distortion will be there, provided by delta modulator. It's not possible. Right, next. So, which of the following combination of step size and sampling rate will avoid slope overload distortion? They are asking us to avoid only slope overload distortion with sinusoidal signals or any signals with non-constant slope, signals with slope, varying slope with respect to time. For those signals, it is not possible to design a step size to avoid all types of distortion. Anyway, you can't avoid all steps of distortion, but choose a proper step size so that you can avoid at least slope overload distortion. Because if you use bigger step size, definitely we can decrease slope overload distortion, or we can avoid also completely. Right. So they are asking about that only. So what is the condition for no slope overload distortion? The condition is differentiation of the signal will give you slope, magnitude of it. Maximum magnitude is what we are interested, because we are talking about only slope overload distortion. Slope overload distortion happens when the message slope is maximum. When the message slope dominates, that is when we have slope overload distortion. Dominates who? Dominates the staircase that we get in delta modulator. Right. So to avoid slope overload distortion, we have to design the step size according to maximum slope of the message. If you design the step size according to maximum slope of the message, that is when we can avoid slope overload distortion. So the condition to avoid slope overload distortion is this is the condition. This is the condition. Okay. Right. Let us substitute. So what is the maximum magnitude of the slope? We can derive a formula also, am cos omega mt. If you think of, if you take the differentiation, we get the maximum magnitude as am into omega m. If you want, you can just go with the basics also. If you differentiate, it will be 10 into 1000 pi into cos differentiation is minus sign magnitude should be less than or equal to delta into 1 by ts is fs. You can write it as fs. 1 by ts, I am writing it as fs. So the maximum magnitude of slope of the signal is 10,000 pi is less than or equal to delta into fs. Fs is also not given in the question, so the condition that should be satisfied. Here they are talking about combination of step size and sampling rate. So what combination of delta and fs? The product of this will be greater than 10,000 pi. So 10,000 pi means what? So this is 3.14. So it is 31,400. What combination of step size and sampling rate will be more? Will give you the product. This product should give us more than 31,400. So this is delta and this is fs. Step size and sampling rate combination they have given us. So if you multiply these two, it is 31,400. Right. And how about this one? This is 40,000, and this is 31,000, and this is 32,000. So if you want slope overload distortion to be avoided, the product should be greater than 31,400, which happens in this. It is equal to is also fine. This also it happens. In this also it happens. But the question is not about getting slope overload distortion. We want to avoid slope overload distortion. We don't want slope overload distortion. That happens only if this condition is not satisfied. The only option that does not satisfy this condition is option C. Okay. Right. Next. So 2 more questions will be done with today's session. Right. A binary symmetric channel has a transition probability of 0.7. So let me draw the binary symmetric channel. X0, X1, Y0, Y1. So they are saying transition probability is 0.7. Since they are saying binary symmetric channel, these two probabilities will be same. And we know the line starting from the same point, if you add the conditional probabilities of both of them, it should be equal to 1. So this should be 0.3. So this also should be 0.3. And it is given that P of 0 is 2 times P of 1. And we know that P of 0 plus P of 1, if you add, it should be equal to 1. So it is given that P of 0 is 2 times P of 1. This condition I am substituting here. So it is 3 times P of 1 is 1. So P of 1 is 1 by 3. So P of 0 should be 2 by 3. Sometimes without giving probabilities, they give the probabilities indirectly in this manner. So P of 0 means P of x naught is given as 1 by 2 by 3, right? Yeah, 2 by 3, and P of x1 as 1 by 3, right? Now, what are they asking us? They are asking us to find probability of error. Whatever they ask, I have given you a very simple procedure. If anybody has not attended that class, the last 3 classes were based on binary symmetric channel only. I've done some wonderful discussion based on that topic, so you can go through the classes if you have missed it. Right, first thing is, first find the intersection probabilities of all the lines. In this line, what are the input and output involved? X naught and Y naught. So intersection of those two, P of x naught intersection Y naught, that probability you want. How do you get that? By multiplying these two probabilities. So 0.7 into 2 by 3 is 1.4 by 3. Okay, next, how about this line's probability? So the involved things are x1 and y naught, P of x1 intersection y naught. If you want, you can multiply this probability with this probability. This is P of y naught given x1 into P of x1, which will give the intersection probability. So 0.3 divided by 3. So this is 0.3 by 3, or 0.1 you can say, right? Okay. Next, how about this one? So this is 0.3 into 2 by 3 is 0.2. Next, how about this line's intersection probability? P of x1 intersection y1 is 0.7 into 1 by 3 is 0.7 divided by 3. Yes, we got the intersection probabilities. Now what do we want? We want probability of error. To find probability of error, we should know the decision making. So if you want to decision making, so by looking at y naught, what is the decision that you can make? By looking at y naught, are you going to decide it as x naught or x1? What is the best decision to make? So if you observe, you are receiving y naught with a probability of 1.4 by 3, it is roughly around 0.5 or something like that, approximately around 0.45 to 0.5. Compared to this one, this is bigger probability, very big probability. So we are receiving y naught most of the times because of x naught, and we are receiving y naught less number of times because of x1. So what is the best decision to make? If you make the decision as x naught, because you are receiving y naught more number of times because of x naught, more number of times you will be correct, and very less number of times you will be wrong. Right, this is the best decision that you can make using map criteria. So this is the correct line and this is the wrong line. Or you can say, with this much probability, with 0.1 probability, you are going to receive y naught because of x1, but you are deciding it as x naught. With this probability, you are going to make an error, because with this probability you are receiving y naught because of x1, but still you are deciding it as x naught. Why? Because we don't know what outcome is because of x1 or what outcome is because of x naught. We don't know that, right? So that's why always whenever you see y naught, you are going to decide it as x naught. So that happens. With a probability of 0.1, we might make an error because y naught might be because of x1 and we are making an error. Okay, but with this probability, we are making the decisions correctly. With this probability, we are making the decisions correctly. So probability of error, if you want to find out, just add up the wrong lines. Okay, so we have done the decision making for y naught. Similarly, let's make the decision making for y1 also. So for y1, which probability is more here? So 0.7 divided by 3. So this is definitely greater than 0.6 divided by 3 is 0.2. 0.7 divided by 3 is definitely greater than 0.2. So this is greater. So y1 we are receiving more number of times because of x1. Hence the best decision to make is x1. Hence this is the correct line and this is the wrong line. So what is the probability of error? So here you are making an error with a probability of 0.2, and here we are making an error with a probability of 0.1. So the total probability of error is 0.1 plus 0.2. The total probability of error is, just add up the error probabilities here, you will get the total probability of error. As simple as that. You don't need any formula. Wonderful. Let's move on to the next question. Same question. Find the joint entropy of the binary symmetric channel. Same question I have given you. I am asking you to find the joint entropy. Joint entropy means, joint entropy means it's denoted by h of x comma y, which is given by sigma p of xi yj into logarithm of 1 by p of xi yj. Because it is binary symmetric channel, there are total, means if you expand it, you will get 4 terms. Because it is binary symmetric channel, instead of 4 terms, if you find 2 terms, that is sufficient. Okay. So let's go back to the previous slide because we have already done some calculations. So this we know. So this is what? P of x naught comma y naught, or x naught intersection y naught. So and this is P of x naught x1 intersection y naught, or x1 comma y naught. Comma is same as intersection. And this is P of x naught comma y1, and this is P of x1 comma y1. So we are all having all the probabilities. Okay, though it is binary symmetric channel, yeah, we have to do all of them separately. So we are having all the probabilities. Point is 1.4 by 3, another is 0.1, another is 0.2, another one is 0.7 divided by 3. Okay, so h of x comma y. Let's do the calculation here. Very simple calculation. What is the information in this? If you want to find the information, it's logarithm of 1 by probability. What is 1 by probability? It is 3 by 1.4. And multiply with the probability, same probability, 1.4 by 3. Plus, what is the information in the second joint probability? 0.1. It is logarithm of 1 by 0.1, which is 1 by 0.1 is 10, and multiply with 0.1, multiply with the probability, because we are finding the average information, average entropy. Okay, whatever I have done here, whatever problem formula I have written here, the same thing I am applying here. So we are multiplying the probability, and inside the logarithm it is inverse. The same thing I am doing here. See this? Inside the logarithm we are inverting, outside we are multiplying with the same probability. Like that we have to do for, since there are 4 intersection probabilities, for all the 4 intersection probabilities, just do the same thing. So this one, this funda, this you have to do it for different combinations of I and j. Okay, since we are already having the calculation, I am doing it in this slide only. Plus next one, it is 0.2 into logarithm of 1 by 0.2 is 5, and base is 2 always here. Base is 2 because we are talking about entropies. Whenever we are talking about entropies, the base is always 2. Okay, next last one, last intersection probability. This one, 0.7 by 3, 0.7 divided by 3 into logarithm of inverse of this, which is 3 divided by 0.7. So we have to use calculator. Manually calculating it is not possible, so you can use calculators and calculate, and you can find the answer. Okay, so that's it guys from my side for this concept through GATE series. I believe you guys got benefited through this series. So if any of you have missed any of the lectures, you can go through them. I've given wonderful concepts. It's up to you how you make use of it. Okay, my part is done in giving the concepts to the best of my efforts in the limited time that is given to me. So now it is up to you how you make use of it. Okay, right. If you have any doubts, you can contact me definitely on my Telegram channel. You can just type my name in Telegram, you'll get the channel. You get the group, not the channel. Right. So that's it guys from my side. I hope these sessions are helpful for you guys. Great. Take care then. Good night. We'll meet soon again in some other sessions in the near future. Okay. Thank you.